Hello everyone, welcome to my YouTube channel. So in this lecture, I will discuss about some left topic of the insertion reaction and the reductive elimination reaction. So first, I will discuss other insertion reaction. So the sulfur dioxide is a strongly electrophilic species. The vacant orbital on the sulfur, which can used attack even a electrometal complex. The reaction is detailed and find that the SO2 can give electrophilic attack at the alpha carbon of the alkyl from the side opposite of the metal, which leads to the formation of the alkyl sulfonate ion with inversion at the carbon. Since the anion has much its negative charge on the oxygen, so it is not surprising that the kinetic product of the ion recombination is the alpha bond sulfonate complex. So on other hand, the thermodynamic product is usually the S-bonded bound sulfonate and the approach for the soft metal. So this is the sequence constituted of 1,2 and 1,1 insertion of SO2. A notable feature of this mechanism is that the SO2 does not need to bind the metal, and so the co-electron vacant side is not needed. So it also can attack the rate electron complex. So here the SO2 this the electrophilic is the SO2 is given electrophilic attack at the alpha carbon of the alkyl group. So the alkyl group is attacked the SO2 to form this ion pair, which can give the kinetically product the co-formation erect product or the thermodynamic product, the sulfur containing product. So here the if the O bounded product is formed, that is a 1,2 shift product, or if the say S bounded product is formed, that is 1,1 shift product, and it is a 1,2 shift product. So here the main interesting features of that, the SO2 does not need to bind the metal, so it is a 2 electron vacant site not needed. So it can attack also in the 18 electron complex. So as expected for this mechanism, the reactivity falls as the alkyl group becomes more bulky and a substitution becomes more electron attracting. By carrying out the crossover reaction on a mixture of RS and SR isomer of the iron CP complex, which is chiral at both Fe and the carbon, so very little crossover product, the RR and SS isomer of the sulfonate complex are seen. This shows that the postulate ion pair must stay together, that the intended iron cation allows stereochemical stability. Ion pairing is very common in the organic solvent. These ions seem to have a well-defined solution structure. Ion pairing is probably quite general for organometallic compounds and can have change in reaction products form. So an unusual insertion of SO2 have been reported in a palladium methyl complex where the resulting MeSO2 ligand bridges between the two metals. So here this palladium methyl ligand inserted into the SO2 to form this rigid metal complex. So Goldberg and Kowarskar have described the rare example of O2 insertion into the MX bond in the case of palladium 4 hydrogen in shown below. Here the O2 is inserted between this metal hydride to form this intermediate. So next we will discuss about the elimination reaction. So there are total mainly 4 types of elimination reaction. One is the alpha elimination, beta elimination, gamma, and delta elimination. So most common is the beta elimination in the organometallic chemistry. So beta elimination is the cheap decomposition pathway for the alkyl that have a beta hydride substitution. A 2 electron vacant site is required at the metal, and there is to be roughly coplanar MCCH arrangement that brings the beta hydride close to the metal. So there are total 2 conditions for the beta hydride elimination. One is the 2 electron vacant site is needed in the metal center. That means the metal should be covalently unsaturated, and the metals carbon and hydrogen should be in the covalent arrangement. So that with that arrangement, the beta hydride is close to the metal. So this is the two condition for the beta hydride elimination. A complicating feature of this process is that the alkene open reinsert into the metal hydride, and this give rise to the isomerization of the alkene or the starting alkyne. So as saw in the hydrogenation, the alkene is rarely coordinated to the final product of the beta hydride because it is usually displaced by the ligand that originally dissociated to open up the 2 electron potential site of the metal or some other ligand in the reaction mixture. So rare cases are known in which both alkyne and alkene hydride can be observed directly. So here in this case, this complex here this alkene is inserted between this metal hydride, and reverse reaction is the beta hydride elimination where the alkene is left from the metal complex and metal hydride is formed. So an 18 electron complex has to lose the ligand to open up the site for the elimination, but this process may or may not be rate limiting. So in case the addition of excess ligand inhibits the reaction by quenching the open site, only if the elimination itself the rate limiting, we will see a kinetic isotopic effect for elimination of H over D. By comparing the elimination of LNMC25 versus LNMC25, the appearance of the isotopic effect KH greater than KH implies that CHD bond breaking is an important step. It is a slow step. So here for this reaction, the first L is dissociated from the metal center, which creates a vacant site at the metal center. Then metal beta hydride elimination occurs. Then 1-butene and metal hydride form. Then this 1-butene is left over from the reaction star to again association of the L ligand to form this final metal hydride species. So in 16 electron complex, 2 electron site is usually available except for palladium 2, especially the platinum 02, which tend to avoid the 8 electron configuration. Imamoto and the co-author that the trans palladium L2E2 complex tend to decompose by the beta elimination directly from the 16 tracking material complex via 18 electron transition state. But the phosphate dissociation is open for the beta hydride elimination in D8 alkyls such as platinum L2B2. The related beta cycle in the beta elimination is 10-4 more slowly than the rest, presumably because the coplanar MCCH bond arrangement is harder to achieve. So here in this case, the beta hydride elimination occurred to form this intermediate. From here, the reductive elimination occurred to form this L2P2 type ligand. So Graves and co-author have studied analogous nickel complex in the presence of absence of excess phosphate and have found that here the 3 decomposition pathway, one for each different intermediate, 40 electron for cellular electron. So here on L3Ni reductive cleavage of these two ethylene molecule can happen, and on L is and from here the reactive elimination to form this cyclobutane, and another possibility is the beta hydride, and another L is dissociated from the ligand framework to form this double beta hydride elimination to form this butene. So alkoxide complex readily undergo beta hydride elimination to keep the ketones or aldehyde, accounting for the ability of the basic isopropanol to reduce many metal halides to hydrides with the formation of acetone. So beta hydride elimination of amides and amines to imines also occur, but tend to be slow. So next we will discuss about the alpha elimination. So if an alkyl has a no beta hydrogen, it may break the CH bond with the alpha gamma delta position. The simplest case is the methyl group, which has no beta hydrogen and can undergo only the alpha elimination to give the methylene hydride. So this is while the beta process give an alkene, a stable species that can dissociate from the metal. The methylene ligand from the alpha elimination is very unstable in the free state, so does not dissociate it. So methylene hydride complex are unstable with respect to starting methyl complex, so the product in the alpha elimination can be intermediate in reaction but at the cell down seen in the isolable species. So alpha elimination will, that means the alpha elimination will occur when there is no beta hydrogen present in the molecule. So upon the alpha hydrogen elimination, the methylene molecule is formed, which is comparatively unstable. So here it is very hard to isolate this methylene type intermediate. Only it is an intermediate for catalytic reaction. So for this reason, alpha elimination process is less well characterized than the beta hydrogen elimination. So studies of both molybdenum and tantalum alkydes suggest that alpha elimination can be up to 10 to the 6 faster than the beta elimination, even in case which both alpha and beta have sweetener present. In such case, the coordinately unsaturated methyl complex seems to be equilibrium in the methylene hydride species, which can sometimes trap either by necrophilic attack with the carbon or removing the hydride by reductive elimination with the second alkyl present in the metal. So here this molybdenum complex has no alpha hydrogen. So here for the phosphine ligand dissociated to create a vacant site for the alpha elimination. Then this methylene hydride intermediate is formed. Then again one phosphine ligand is attacked to form this complex. Salk and Kovarskas have found an interesting case of alpha and beta elimination taking place competitively in the tantalum complex. The two are automers of the which can be observed in the solution of ONH. So here this tantalum complex is in the equilibrium with this here for the alpha elimination from this methylene intermediate and the beta elimination from this methylene intermediate. So this is observed in the ONH anymore. So because of the heteroatom can strongly stabilize the carbon, the alpha elimination is strongly referred to beta elimination. A photocatalytic alpha elimination by transfer of hydrogen atom from carbon to an oxo group in CH3RO3 has been in slow matrix, slow temperature matrix. So next we will discuss about the other elimination next. In addition to alkyls, a great variety of other ligands have no beta hydrogen, but we have the gamma and delta can undergo gamma delta elimination to give cyclic product. Some example of this cyclometallic reactor are shown. So here the iridium PMET PPH4 here there are no alpha beta hydrogen present. So here the alpha beta gamma hydrogen eliminated to form this metallocyclopesis. For similarly for MECN CO5 here the PCH2ACME for this case here delta hydrogen is eliminated to form this metallocyclopesis. So also in this case the iridium complex the gamma hydrogen is eliminated to form this cyclometallopesis. So this elimination reaction can be taught as a being related to the oxidative addition of a CH bond with the metal. This is seen more clearly for beta hydride elimination if right in the metal cyclopropane from two of the alkene hydride product. For the alpha elimination, the consider H2 from the product carbon hydride. Both gamma and delta elimination are more obvious example of oxidative addition. So here the beta hydrogen from this metallocyclopropane and this alpha elimination from methylene intermediate. So neopentyl platinum compound tend to decompose by the gamma elimination in contrast to alpha elimination found for the tantalum complex. This may imply that the mechanism in the two cases is different. For example, tantalum case alpha bond metathesis is possible in which the one alkyl might be decoordinated and activated alpha hydrogen by a second alkyl group rather than undergo oxidative addition to CH1, which is more prevalent for low valent platinum related to the example of gamma delta elimination. So here this platinum complex gamma elimination gamma hydrogen elimination occurred to form this metallocyclopropane. And then here also for this case, this platinum, this case gamma hydrogen elimination to form this product. There are many possibilities for this type of. So this is for the elimination reaction.
So now I will discuss about the ligand substitution reaction in the organometallic chemistry. So many synthetic reactions require the substitution of one ligand by another. So reaction in which coordinated ligands are displaced by the other ligand are termed as a substitution reaction. Such a reaction is often the first step and sometimes the determining step in many stoichiometric and catalytic reaction of organometallic complex. So in fact, a site of coordination and saturation is perhaps the single most important property of homogeneous catalysis. So a substitution reaction in organometallic chemistry in which an existing ligand on a metal center is removed, its position gets occupied by another ligand. So this way, the way this occurs depend on the factors such as the geometry, electron count of the metal complex, the existing ligand on the metal, and their static and electronic properties. So substitution reaction occur by the combination of ligand addition and ligand dissociation reaction, and a range of possibility exists for such reaction. At one extreme, the departing ligand leaves a discernible intermediate with a lower coordination number is formed, and the mechanics level is D for here D for the dissociation. At the other extreme, the incoming ligands add to the complex and intermediate with the increased coordination number is formed, and the mechanism level is A for the association. So a continuum of the possibilities stretch between these two extremes. For example, interchange I is used for the incoming ligand is presumed to assist a reaction, but no detectable intermediates appear. When the degree of assistance by the incoming ligand is small, the reaction is primarily dissociation is called the dissociated interchange, that is called ID. And when the incoming ligand begins to form a bond with the metal center before departing ligand bond is weakened, applicably it called the associative interchange IA. Whether or not a organometallic complex is covalently desaturated, it is important in determining the mechanism by which it undergoes the ligand substitution. The exact mechanism of the ligand substitution, which may occur either by associated or by dissociated route, depend on the large part on the electron count on the metal complex undergoing the ligand substitution. So in 18 electron coordinately saturated compounds, substitution often occurs through a dissociative pathway, while a coordinately unsaturated compound, its often occurs through a associated pathway. So sometimes few dissociation pathways. So most of the substitution involve two electron pathways, radical pathways involving odd electron also known, but are the less common. So the ligands, so that means the ligand substitution reaction is a ligand substitution reaction means a ligand in the metal framework is substituted by the another ligand. So the way this occur depends on the factors such as the rate of the geometry, electron count of the metal complex, existing ligand of the metal, and their steric and electronic properties. And the substitution reaction can be occur via two way. One is the associative mechanism, one is the dissociative mechanism. So associative mechanism means when the metal is covalently unsaturated, that means it is a 16 electron complex. So in that case, the associative mechanism is operated. That means there is an increase in the coordination number in the substitution reaction. And another one is the dissociative mechanism. The dissociative mechanism occurred when the metal is a covalently saturated, that is means it's a 18 electron complex. So here the substitution reaction occurred via the first departure of a ligand, then the new ligand is attached to the metal center. And another type is the intermediate interchange mechanism occur when the incoming ligand and presumed to assist the reaction, but the non-detectable intermediates appear. So now I'll discuss about the activation entropy and the activation volume. So kinetic studies can often provide the indicating the regarding the nature of the reaction, associated, dissociative, or the interchange. So reaction kinetic study indicate that the reaction have a large negative activation entropy, negative activation volume are indicating the associative mechanism, while the reaction have a large positive entropy and positive reaction volume are indicated a dissociative mechanism. So for interchange mechanism, S and B should be very small or close to 0. So if the reaction rate is depend on the incoming ligand, it's indicate a associative mechanism, while no such dependence existent for a dissociative mechanism. So that means for the associative mechanism, there is a positive, negative entropy and negative activation volume, And for the dissociative mechanism, there is a large positive entropy, activation entropy, and activation volume is present. And for the associative mechanism, the reaction rate depend on the incoming ligand. So here depict all this type of mechanism in a ring plot. A ring plot is usually made after carrying out the kinetics at different temperature from the intercept of the plot activation energy, and can be explained and determined. The knowledge of this activation volume, the difference between the partial volume of the transition state intermediate and the sum of the partial molar volume of the reactant is important in the reaction carried out under high pressure. Those reactions having the large negative activation volume are accelerated by high pressure, as the volume of the intermediate transition state will be smaller than of the reactant. So molar volume is obtained from this plot ln versus P. So here this is a substitution reaction where mln x plus y equal to mln yx. So here for this dissociative mechanism, first for this dissociative mechanism, first the x is dissociated, then mln intermediate form, then the upcoming ligand associated with this metal complex to form this mln y. And for the associative mechanism, mln x, first the incoming ligand is associated to form this intermediate mln xy, and here next the x ligand is departed to form this final product mln y. So this is a associative mechanism. It possesses a delta s is a negative, and for the dissociative delta s is equal to positive. And the interchange mechanism is that where mln x, here first y is attached. So here a transition state where simultaneously bond breaking of mnx and the bond making of mny is happened, then x is departed to form this mln y. So this is the interchange mechanism where delta s is close to 0. So here is the iron plot for the determinant of entropy. So here ln x by t by 1 by t. So which from this plot we can calculate the integration entropy. So it is observed that the 17 electron complex undergo ligand substitution reaction much faster than the 18 electron complex. For example, VOCOL6 undergo substitution by PPH3 at the -70° C in 90 minutes, while the VOCO-6 does not need even in the molten PP. The substitution of VO6 is 17 faster than the CrCOL6, while the 17 electron VOCOL6 complex undergo substitution in the associative mechanism, the preferred pathway for high temperature in a dissociable nature. So as a 17 electron species undergo the ligand substitution at the higher rate than the 18 electron species, the latter can be oxidized to generate a substantially labile 17 electron species. So factor affecting the substitution reaction. So the first one is the steric factor. So the dissociative mechanism that is observed in a 18 electron complex may be operate in the 16 electron complex as well, when this complex either have the sterically bulky ligand then that block an open coordination site, or then they belong to the third row square planar D8 complex like platinum, where the strong electronic factor limit the coordination of additional ligand to empty axial site. For example, the large PCY3 ligand sterically block the access of the empty axial PZ orbital of the nickel complex. The PT complex turns the coordination of the incoming ligand via the PZ orbital is partially blocked by the field DZ star of the platinum. So this limit the ligand association, although it can be logically occur, hence the substitution occurs via 3-coordinated intermediate. So as bulky ligands occupy more space around the metal center, can block the incoming ligand that are trying to access the vacant coordination site on the metal. They often dissociated to relieve the steric strain. Consider, for example, the following equilibrium reaction wherein the dissociation of the bulky phosphide has been found to be more facile. So the dissociation of PPSC from many complexes such as nickel PPSC whole 4, PD PPSC whole 4, RHCl PPSC whole 3 is well documented in the catalytic cycle involving these catalysts. The replacing the PPHC by PT3 in the equation catalyst result in the inactive catalyst as a ligand dissociation become very difficult due to the strong pyridium PB83 bond. So here this is a square planar complex. Here the substitution is first dissociation of this chloride, then the bromine is attacked. So here the ligand dissociation is occurred via the dissociation mechanism rather than the associative mechanism. So substitution reaction of the square planar particular complex. So here nickel PR3, the constant for the ligand dissociation for when this PO toluene or PI isopropanol, the dissociation extent of dissociation is greater compared to this. So next one is the trans effect. So in 1926, Russian chemist discovered that certain ligands facilitate the substitution of a second ligand turned to the first by an external ligand. The ligands that are more effective at this levelization are said to have the higher trans effect. The effect is most marked by in the substitution of platinum to complex, and the higher trans effect ligand found the either strong single one such as H minus, Me or SN3 or strong pi one such as CO. The trans effect function the electronics effect of the one ligand to other when they are located trans to each other. If it involves the two sigma donating ligand, the stronger ligand preferentially weakens the bond of the weaker sigma donating ligand turns to it, thus making it easier to dissociate to bring about the ligand substitution reaction. So here this L ligand is a Cl is a turns to the L ligand. So here the dissociation of the Cl to and then again the substitution of the pyridine. So here the substitution, the dissociation of Cl is depend on the trans effect of the L. So here when the ligand has the H minus has a higher trans effect, so that case the ligand dissociation is higher. So trans effect can be so the well-known example of trans effect is the synthesis of anti-cancer drug cisplatin. The starting for PTCl4 minus, the first NH3 ligand is added to a Ne4 equivalent position, and then about the second NH3 added only to the cis to the first one. And this happen because Cl is a larger trans effect than NH3. So if on other hand the ones start a PNH4, the trans substitution product is observed. So here the when the cisplatin is a transplatin is a cisplatin. So here the when started with the platinum CCl4, the first NH3 ligand with the substituent the one Cl, here all Cl are equivalent. So next the trans effect comes into the play into the role. So here between the NH3 and Cl, the Cl has a higher trans effect. So here the Cl will be dissociated to form this cisplatin, and for when the NAPT NH3 all for 2 plus is with starting material, so that case first the Cl minus is coordinated here in any position. Next the Cl minus has a higher trans effect compared to the NH3. So here the another Cl is coordinated to the trans to the this Cl, so from this transplatin. So trans effect of the pi acceptor ligand, the bond between the pi acceptor ligand and the metal having 2 or more d electron is weakened when there is another pi acceptor ligand turns to it. In the metal carbon, the competition between the two trans pi acceptor ligand or the same d electron reduce the amount of pi bonding, therefore the weakens the MCO bond. Conversely, the MCO bond is straightened when the CO is turns to a good sigma donating ligand that cannot be pi bonded. Similarly, the MCO bond is straightened when CO is turns to any pi donor ligand. So as one CO is ligand is replaced by with the good sigma donor PME3, the next CO substitution becomes progressively more difficult, require higher temperature and longer time. On the CrCO3 PME3 is formed, it is extremely difficult to replace another carbonyl ligand because the CrCO bond strength increases enormously. So next we will discuss about the associative substitution. In the associative substitution reaction, the incoming ligand first add to the metal complex, then the dissociation of one the original ligand occurs, the unsaturated complex is typically required to in order to propose such associated substitution mechanism, though the axial digit square orbital can partially block the coordination of the ligand using the empty pz orbital in the third orbital. This does not occur in the rhodium or palladium too, and the ligand dissociation is common in these complexes. So scheme, so the associative substitution reaction can in a sparkle and rhodium complex, the two different products are possible in this reaction. As Cl minus being relatively weak ligand can be substituted by PMEC. So here is a 60 electron complex. Here the PMEC is come to form this 80 electron 5 count 8 electron complex where Cl minus can be dissociated or PMEC can be liquidated to form this final product. So the stereochemistry at the metal center is open. Is stereochemistry at the metal center is open retained at the simple associated substitution follow a second order rate law, and the negative entropy of the activation is observed, and oxidation addition also come under the associative mechanism is indicated as a negative activation entropy. For example, delta S for oxidation addition of H2 to Haskell complex has been determined. Associative mechanism seldom observed in the 18 electrons complexes. However, in polythyroid ligands that can adopt a lower heptacity is present, it occurs the indole effect, the fluorine effect of the heptacity lowering the associated nita 5 pentanyl as well as the nita 3 alkyl complex discussed below clearly indicate the way in which the electron complex undergo ligand substitution by associative mechanism. So heptacity change in the multi-entangled ligands, a factor which often influence the associative substitution reaction in the organometallic complex, is the heptology change in the multi-entangled ligands. The multi-entangled ligands can often change their coordination number to the donate fewer electrons, thus opening of the coordination site that can allow to associative substitution. The CP ligand can do this by shifting a heptacity from nita 5 to nita 3 but this shifting incurs the moderately high cost in energy due to the loss of the aromaticity in the CP ring. Such heptacity change are not the common for CP. So indole and fluorine effects. The indole ligands family, however, they are dramatically change the rate of substitution reaction due to his ability to switch the aromaticity between the CP and the arene ring via following resonance structure. This dramatically lowers the barrier to nita 5 to nita 6, thus upcoming opening of a free coordination site and allowing easier ligand addition to the substitution reaction. So it is indole here. This can be the nita 5 mode or be in the nita 3 mode. The reaction is given which needs by the associative mechanism is 10 to the power 8 times faster than the reaction of the analog complex posing the only CP ring. So here this rhodium complex, the electron complex, here the CP ring is the nita 5 mode. When it follow the associative mechanism, so that case it follow the nita 3 CP3 converted to nita 3 mode, then PPS3 ligand in coming and the dissociation of CO to follow this 16 electron complex, then this 18 nita 5 18 electron complex is formed. So the reaction of nita 5 CP NOCO3 with when attempt for 3 days in decalin at 143 did not proceed. However, the analogous Indian complex undergo identical reaction condition will to this Mn nita 5 C3. So extending this study to the similar ligand indicating that the fluorine ligand accelerates the ligand substitution reaction by factor of 10 to the power 10, although the indole effects would be theoretically generated better catalyst due to stability to readily open up a free coordination site on the metal. So in arthrophysiology also makes the Indian link constantly easier to displace from the metal. So here some comparison where the indole and the fluorine ligand has a higher rate of the ligand substitution reaction in the associative mechanism. And also the heptacity change in the pentadiene ligand. The pentadiene ligands are the cyclic fraction of CP minus does not have any aromatic stabilization. This has two important effects. No aromatic stabilization means that the pi orbital is higher in the energy and therefore better donors than the CP minus, and barrier for nita 5 to nita 3 and nita 1 coordination is much smaller energy. Two and second one, the pi star anti-bonding orbital are the lower in energy and the better pi acceptor than CP minus. So here the rhenium CO3 at the nita 5 mode when it is come to the ligand substitution reaction, so nita 3, and upon elimination of CO, so it forms this nita 1 mode. The heterocytic change in the allylic ligand, the allylic anion has a similar facile ability to switch between the nita 1 to nita 3 coordination mode to can promote the ligand addition or substitution reaction. So here the this allylic ligand is come interchange between nita 1 and nita 3 to form this ligand substitution reaction. So next one is the dissociation substitution. So dissociative substitution is commonly referred mechanism of the ligand substitution of covalently unsaturated saturated 18 electron complex. We do not possess ligand capable of easy electricity change. So 18 electron octahedral metal complex invariably have a dissociative substitution pathway. One of the existing ligand on the metal falls away, create a free coordination site to which a new ligand can coordinate. So dissociative substitution reactions usually have the positive activation entropy. Example of both reaction as well as the inversion are known for the dissociative substitution reaction. Dissociation of the ligand also depend on the static effect. So here it is the 18 electron complex. It is a covalently saturated molecule. Here the first CO dissociation to form the 16 electron complex. Next the ligand substitution reaction by the association of the PME3. So in this case also the NiCO first dissociation of the CO, then the upcoming ligand is associated to form this NiCO3 PR3. So the racemization of the chiral or commutative complex occur by the dissociation mechanism. In the following example, the loss of phosphine give a tri-coordinated functional intermediate which can give rise to both the enantiomer upon detachment of the phosphine. So next one is the interchange mechanism. So dissociation and associative interaction mechanisms are observed in the substitution reaction in organometallic complex, but not very frequently. It has been observed that the formation of the 20 electron intermediates upon the reaction are unlikely, but the 20 electron transition states seem possible, unlike the intermediates which is described as a species which has no survived as the independent entity. Often briefly transition state has much shorter lifetime, which is comparable to the molecular vibration. Such transition states are common in interchanging the mechanism. Detailed kinetic studies and careful determination of the activation entropy are required to differentiate between this IA and ID and AD mechanism. Often slight variation in the steric and electronic capability of ligand in the metal complex resulted in change in the associative mechanism or interchange mechanism. So associative interchange. So in this tantalum complex, when the DME ligand is replaced by the 2 pyridine, the mechanism change from the dissociative to associated interchange. So in this metal complex, and this ligand is replaced by the acetylene group. Here this associative interchange is from the following this metal complex. So next one is the interchange in dissociative interchange. So in a 18 electron vanadium complex, this one changing the cyclopentadiene ligand in the pentadiene ligand results in the interchange from the associated to dissociative interchange mechanism as indicated by the reaction entropy values. So here this vanadium upon the it is a associative mechanism. So here the CO is bound. So this is the associative mechanism, but for the dissociative interchange ID, so here this molecule is here the CO ascorbyl ligand is bonding via this transition step to form this final product. So this is the brief introduction about the associate ligand substitution reaction, which can occur by the association or dissociation pathway or by the interchange pathway. So thank you.